Good afternoon. We have two lectures to go. The first one will be Tsvi Lev, Corporate VP and Head of NEC Labs in Israel. And he will talk about explainability beyond the hype.
Hi everyone. I'd first like to know the audience a bit. So, how many people here have actually worked in some way, shape or form with AI models? Training them, deploying them? Okay, great. And how many of you, pardon the question, actually had a customer for that? In the sense, and I will differentiate. It doesn't mean if someone was paying for it, but if there was someone, a recipient of your model that was not you, and may have had remarks or requests for improvement, unlike what's known as SOTA papers, where people say there is some SOTA on something no one cares about, we improved it by 5%, and then there is no customer because there is no one actually using it and telling you I have issues. So how many of you have deployed or gave your models, just like the previous lecture where they gave their model for VPG, this unit, and they have to actually use it to find bugs in their production? So how many of you have had this experience, the interaction? Yeah, I'm not surprised. Okay, about a quarter. Okay, so that's real life. In real life, people actually use your model. When you look at the academic landscape, there's so many, literally hundreds of papers about how to train AI models. Everyone is obsessed with a new filter or a new parameter way or a new loss function. But there's comparatively very little about the world of what happens when people actually use it, and you have to qualify. I mean, you have to convince them it's good enough. That's the world which really, of course, affects the industry and the world. The rest is not important. It's just it's a step. It's not the end target. So just a bit about NEC, really just 2 lines. So NEC also was once a startup. You can see the Asian guy on the left. That's the founder of NEC. That was 120 years ago. We celebrated this July. And this was a startup managed by someone called Thomas Edison, which later became General Electric, and NEC started from that in Japan. I think a lot like IBM, which is also, it's a little younger, but it's similar in longevity. We invest a lot in core research. So one example which is pertinent here, we do supercomputers, we do spacecraft that go all the way to asteroids, we do carbon nanotubes, but also the one in the middle, the upper middle part, some may recognize it was done by a young researcher in Princeton Labs in 2003. 10 years before ImageNet, AlexNet and all that. And he had the idea to use convolutional neural networks to do face detection in video. And the video, by the way, you can still find on YouTube from 2003. That was in our Princeton Labs. His name is Yann LeCun. You may have heard the name. Recipient of the Turing Prize. But he's no longer in NEC for many years. The Israeli Center, I established it 3 years ago. I report to the company CTO, Global. And we revolve in whatever we do about applied AI, meaning everything we do in AI has a customer. Doesn't matter if it's internal, external, proof of concept, but it's always designed so it will be used by someone and we get their feedback. So that's our specialization. And by the way, we're still growing. So if anyone's interested in applying AI to cyber, to medical, or to vision, you might want to come to me later. Okay, now let's get to the subject at hand. Okay. So let's start. When you read papers, especially in the last few years, there are so many papers. You need AI to summarize and find if any of them are of value. People always talk about the AUC curve, right? Specificity, precision, accuracy, and these parameters. And it makes sense, right? When you look at how AI started to be used, it started to be used historically in real production for recommendation engines, showing you ads or recommending movies on Netflix or similar things on IMDb, just for your interest. And what you care about there is hit rate, right? I mean, if I show you 5 ads and you average click on one of them, and before I applied AI, you clicked on maybe 0.1 or 0.5, I improved my numbers, right? Every little improvement in the success rate is more money. When you look at ImageNet and the improvement also, everyone was talking about the accuracy, which makes sense. However, people started asking questions which we are not going to get into here about things like bias. They said, okay, maybe you get great accuracy, but maybe you show people who come from different backgrounds or have had different life experiences, different things, so you show the good ads with the exciting deals only to a certain part of the population. That's a whole area. I will not be talking about that now, but that shows you that just accuracy is not the only thing. When you talk about automotive, again, people say, okay, if I reduce the number of accidents on average, is that enough? Well, absolutely not. Okay. For example, people care about stability. What happens if you didn't train for this scenario and Mount St. Helens in Washington state erupts again and there's this ash in the air and you never thought about training for that, and suddenly in one day your average precision or accuracy in the car is not the high number you expect, but a very low one. That's really bad. If you don't know what affects your algorithm well, then how do you know to predict what kind of QA you need to do, except for doing a lot of QA, which everyone says they should do, and they do. When you talk about healthcare, it's even more complex. You did a 3D, these are all very realistic scenarios, some of them involving projects that we are doing right now. You do a 3D lung CT for a 55-year-old male who's been a heavy smoker all his life, and you find a lump, a small lump. Now you have to make a decision, do I do a biopsy or not? It's an important decision. It's not only the pain and the money. About 1 to 1.5% of these cases, when you do a biopsy, it actually complicates the situation of the patient. Things go bad. So do you take this risk on this person? When a physician does this decision, well, at least you have someone to blame. But if the AI tells you should do the biopsy, who do you blame? So taking into account, it's no surprise. I'm going to be giving similar talk in 2 days in Open Data Science in London, and I'm not the only one talking about explainable AI there. There are several others. It became very hot, and Gartner pretty much says, if you're going to apply AI in production, you have to make it either explainable or to show why you think it will be robust and why you think you comply with regulation, and probably you need to do all of these 3 things. So just accuracy is not enough, and the quote below is by a really big vendor who is deploying AI in production, and they say the same. So the ones not talking about this at all are the internet companies selling you advertisements. They don't talk about it at all. They don't think there is a problem. Everyone who's actually trying to apply an AI in things that matter does have this problem. How do you solve it? Or how do you think about it? Okay, just a moment. Just to show a few examples why without explainability, without understanding what your model does, things can go bad really well, even if you have your precious accuracy and ROC curve and AUC curve. This is a good example. I know the screen is not great. I hope you can see it. This is dermatology. It's actually looking for cancerous growth melanomas on the skin. Okay, so I hope you can see it. From my distance, it's very hard to see. So there's something which is suspected as being a melanoma here, and you show this part of the picture to the algorithm, which was trained well, and it says benign. Then you zoom a bit, and the blue marks are not blue skin. Okay, actually, in many cases, dermatologists mark in some countries, in some areas, with blue, the areas which they think warrant further inspection. Now, no dermatologist would come and say, oh, this blue is cancerous. But the algorithm, which was trained to very high precision and got a very nice publication, and if there was a PhD involved, I'm sure they got the grades and everything, but they never thought that people do that because there's a lot of physicians in the world and they do things differently. So the algorithm says it's malignant. And when you zoom in, it says, oh yeah, okay, it's benign. So imagine now you are deploying this in a commercial product, in a place, in a lab, in a region of the country, in a different country, where people use these blue markings, okay? Or maybe they use black markings, and your algorithm never knew that this is something you should train for. That can be a real problem. Another example from the NLP world, Again, NLP is used a lot now to choose advertisements or all kinds of fancy names for the same thing, which is to show you some more advertisements. They have many names for it. Then it doesn't matter so much. But here is an example. A lot of work on medical AI right now revolves around trying to extract information from text which is already there. What happens is you have unstructured data. You have long medical reports. For example, in oncology, oncological cancer treatments, there's long reports with a lot of data which physicians and nurses fill in. It's not structured. It's not well-defined fields. And you need suddenly to extract some very simple thing from it. A good example is you can go now to the general manager of a big hospital and ask him, can you tell me how many patients you have right now undergoing treatment for liver cancer? You would say that's a rather simple question, right? They have no way to tell you except for looking at all the records and figuring out, because it's not written in the headline. It's something that if you're a physician and you read, then you can understand well within 30 seconds or a minute. But it's not structured like that. So they did, these people developed an algorithm which could read an ongoing oncology treatment report and tell you some very simple things, factual things, not predictions, about whether some procedure was applied or not and whether it was successful or not. They trained it in Seattle and it worked. You can see the numbers here very well, 90.95 to 1, very well. Then they took it to a very exotic different place, a hospital in Kansas, and it didn't work at all, okay? Now, by the way, can anyone here does NLPI? Can you guess why? So different? Yes, but it's even more different people. How many oncologists do you think you have in a big hospital like that? There's maybe 5, maybe 10 people, and they have the terms. They all use the same medical terms in general, but they phrase their sentences in a certain way because that's how we all do. And then you move to a different hospitals, and these people just phrase their sentences slightly differently. Okay? So this is just to try to show you that it is important to understand what the AI does, or at least be able to quantify it. And there's other problems. There's problems of distribution of errors. If you have a current process, like the process which was described for people finding problems in video game, in the video rendering of computers with a new driver, they may miss some cases, they may find some cases, but overall, over time, it's supposed to be rather average performance. You expect some stability. You don't expect them to work perfectly for a whole year and then one day to have 1,000 false alarms. Okay, it's very hard to think about any process you were involved with in school, in the army, in industry. You always expect a certain level of performance. If some tiny thing changes and suddenly your behavior changes very much, the average, the long-term average doesn't matter anymore. You have a problem right now, and it's a big problem. So fluctuations in performance are also an issue. Okay, I think if anyone doesn't know these cases, so the examples are showing one, which everyone is talking about right now in the academic world, is adversarial attacks, where you find that you add some very small noise to an image, and suddenly the classification results changes completely, right? So that makes people nervous if they have to actually deploy this for something which is more important than showing advertisements. Up here, you can see another example where you have those object detection, famous object detection algorithms like YOLO and MobileNet and the others, and you change something very tiny in the video, and suddenly they find a gazillion different objects which are not there, and the algorithm crashes, okay? So these things are not reflected in terms like accuracy. So summary of why we care, and then what you can do about it, okay? The ones on the left, where a single decision by the AI can have a large impact on life, on money even, that's where organizations tend to demand explainable AI. The things no one really cares about except if they make money, and it's small amounts every time, then you don't need it so much. You still would like it, but you don't need it so much. So, people have tried, this is a DARPA. DARPA, as in many things, were one among the first to work on those things. So they tried to give like explainability score to different models. They said, okay, a decision tree or rule-based is something we can understand, okay? But deep neural networks are not. Well, I'm not sure. This is work by Hinton and partners, where they show that you can do amnesty. Everyone here's amnesty is just a handwritten digit recognition, one of the sandbox example everyone plays with in the first or second course. So you see here a set of templates. The algorithm is very simple. At each point, you take your input, you cross-correlate it with this template. If it's above certain threshold, you take the right. If it's below, to the left. And as you can see, within 5 stages, you can actually do classification. And the performance is quite good. It's not as good as the latest, but it's quite good. But do you understand it? I'm not sure I do. So the model, the algorithm used as your model doesn't guarantee anything. So the guys from DARPA made analysis of what we really mean when we say explainable, which is usually the thing people say when they don't want to apply the AI right now in production. And they characterized. And there's a few things here, okay? One, which some of you may have encountered, that's the most associated with causality, is with explainability, is causality analysis. Meaning you're saying, okay, there's 1 million parameters, like the pixels in the image, which made me reach some conclusion, but is there some small group of them which made me reach the conclusion more than the others, okay? That's causality. So like, just saying it's all the pixels doesn't matter, but if you say, okay, those pixels here which look like the eye of a bird, that's what made it think it's a bird, that's causality, okay? Another one, to know when you fail, is reliability / abstention, meaning can I associate a confidence level to my output so I know whether I want to trust it or whether I want to say I'm abstaining, meaning I'm not using it, okay? In many real-life processes, all the ones I listed on the left, actually no one needs them to be automatic all the time. It would be great if they're automatic, but it's much better that in some cases they will say, you know, I'm not sure. I mean, think even about the example that Intel gave. Let's say the algorithm runs and says, you know, on 50 cases, I'm sure this is an anomaly in the driver. There's 3 I'm not sure about. Please have a look. We still have people to do that, right? We used to use all people. So that's not a problem. And the last, and maybe the most important one, is model improvement. Meaning, you have an algorithm, you got some result, you publish your paper. Now you come to your user or customer. They've got some qualms. They say, okay, yeah, it's nice, but look, here, why did it say that? Why did it say that? And they're not really asking why. They want you to fix it, right? Anyone here has been involved with this iteration? How many people here had actually had to iterate? Okay, far less than the people doing AI in some way, which is natural, okay? But let me tell you something. That's the part which separates the ones who succeed from the ones who don't. Just to publish a paper which you improved some general parameter, nobody cares about it, really. So causality, I don't have time to go over it, but let's just look at the picture below, and you can find many papers like that because it's very visual. People like talking about it. It's very easy to understand, and it's useful. You find there are many different ways, like climb. I'm just mentioning it here for you to read, and there's many follow-up works since, which basically allow you to find regions in the picture which were the most pertinent to make the classification. Sometimes it gives some insight, but you can't really fix anything with it, right? You get some good warm fuzzy feeling you may understand, but still, if the customer is not happy and said, you said that's a Labrador, that's not a Labrador, not much you can do about it. Reliability and abstention. Actually, we did work on that, and we've shown it last year, not in this session, and that was quite nice. There's a guy who works now at Google who did also some work on that, and I will try to give you the intuition. No time for formulas, but still, for everyone, if you know that the way modern classification networks for image works, there's the last layer, which is actually the classes, and almost always before it, there's a layer which is fully connected with a lot more neurons, right? Okay? Usually we don't care about that. We say, okay, that's part of the network. Turns out that this layer is interesting, right? I mean, it's very easy to understand that if 2 images in the input give exactly the same output in this middle layer, exactly the same or almost exactly the same, they will get the same classification, okay? Okay, so that's good. But actually, there are many different subclasses that will get the same classification and are not the same in that layer. So it's an area where you can do clustering and you can do analysis. What we did and show that it can actually improve the results is when you look at this last layer, one before last, you look at the values. You have a vector of 200 numbers or so, and you compare it with some simple measure, distance measure like Euclidean or Euler product or whatever, to all the training data, to all the training vectors you got from running the training data on that network, and you find the nearest neighbor or nearest neighbors. Okay? If they're from the same class, you have a much bigger reason to believe that you are right. Okay? So inputs that look the same on that layer, on the one before last layer, are inputs that can serve you to, like, as past examples or labeled examples to justify or actually to lose belief in what you're doing. Okay? So we use this to be very numerical and precise. What we did with this was we did abstention, meaning if the vector, if we got a new input vector, whether it's because of an adversarial attack or just because it's a new kind of sample, and this vector, the before last layer, was very different from all the training samples, according to some distance measure, we said we abstain. We are not saying what it is, we don't know what it is. That's very important, right? I mean, if you've done any classification layer, the one thing they never show you on ImageNet or MNIST is the most important class, which says, I don't know, it's not one of these classes. It's a big lie, okay? I show you a smiling face to MNIST, it's not going to say, hey, that's not a digit, which every kid will say, it's what's going to give you a result. That's not great. So abstention is important. As I mentioned, that's part of the reason why people want explainable. They want to say, first of all, can I trust it? But now let's try to go in here. I won't have time to get into the detail. I'll give you the gist of it, and who wants to know more is more than welcome to talk to us. But basically, now let's talk about the last and the most important, valuable part of explainability. How can I improve it? So what is the process? You develop the model, you run it, you got a result. The customer says, sorry, on this example, I think you're wrong. Now forget about networks. If you are a guy doing the classification, and you're trying to explain why you got it right, and you think you got it right, what would be the most common answer you would give if you can give it? You will say, it's just like the case we did yesterday, right? I mean, you don't need AI. It happens everyday life, right? When we think some example is very similar to previous examples that where we had to make some decision, we say, it's the same. Judges love that, right? Judges, in Israel, no, but usually judges don't like to be innovative. They like to say, okay, I found actually 20 cases which are very analogous to this one, and that's what should be done. Doctors don't like to be innovative. They like to say, okay, this tumor looks so much like the previous ones, I think that's what it is. But how do you do that? Okay, we defined it would be very nice, like this example, if your AI can show, it's still not explaining, it just says, look, I think this one, the one in the blue, is similar to those. If you don't agree with me, then I failed. But if you agree with me, then I'm right, okay? Now, how would you usually do that? If you were to try to compare the images themselves, that's banal, right? It's like, of course, if they look the same to the eye, just exactly the same, it's the same case. What we're saying is, imagine you can find the most similar cases based on the before last layer. Remember that layer? So you go back to your training set and look at the cases which got very similar vector in the layer before the last one, and you see what they appear like. Those should be your reference. If they look according to the classification the right way, then you have your explanation. So you can see here an example. So basically, amnesty is the easiest. Where is that very useful, and where have we not applied it well so far? And I'm not sure we can. This is very useful when you talk about geometrical shapes, things like blobs, tenuous material. It's very good for localized features of medical areas. And it's good for things like digits or letters, but that's not so important. I don't think we know how to apply this to ImageNet, okay? You have a picture of a parrot, and you have maybe 10,000, if you're lucky, previous pictures of a parrot. There's such a big variation in angle, in shape, so the ones it will think are similar will not appear meaningfully similar in any way. But things which usually have the same parts, like car or human skeleton, meaning like pose in space, not the physical skeleton, okay? Things like faces, things like digits, and things like pulmonary nodules in lung CT, they tend to look like that. When you see what radiologists, for example, do when they look at images, how many, people say, to train AI, you need 10,000 examples, for example, on some radiology problem. How many examples do you think are shown to a radiologist so they'll start to work? Any guess? Think about it. What's done? No one thought about AI. They have a book, right? In the book, if you're lucky, there's 10 images, and they start training. And they make a few mistakes. They don't make 20,000 mistakes. When they're resident, they do so many things, and they're so tired. So at first, they're not sure. After maybe 10 more examples, 15 more examples, they're supposed to know how to do it. They might not still be great, and there might be rare cases, but they're supposed to know, right? So basically, what we are saying, in order to have full explainability for some problem, it's a recipe, but of course this recipe has to be redone for any problem. I'm not giving you the formula, I'm giving you the recipe, and in some cases we succeeded to do it, okay? Basically, you have to be able to find the similar past cases based on the one before last layer, and then you have to develop or invent a transformation between the two. So look at the digits here, which seem to be briefing. They start with a digit which was given for classification, and they end with an existing labeled example. And the flow between them is the transformation you had to generate. Luckily for us, we didn't have to invent this transformation from scratch. It's a very thriving area of research in medical. Okay, why? Because in medical, you have current pictures of a person, of the lung, or of the liver, or of the heart, and you have previous ones, and you have to try to correlate them. So there's been dozens of excellent works on how to deform some similar images from one to the other. So this can make a nodule or a lung look like a different lung. If you try to apply it to a picture of a parrot and a different parrot, it will not work for you. Okay, let's see. We have 2 more minutes, so basically just to show you an example of how this works in real life, and I'm just going to show Omnis. I wish I could show you the medical area, but just to explain what you see will take a while. So here's an example where we had the new sample here. It's a 0. Don't ask me why, but that's a 0. The customer, okay, said it's a 0, and we actually didn't classify it right. And the customer said, why? What's the nearest example? We said, okay, so the one on the right, the labeled sample, was one which we did classify as 0. So we have an example where the customer said, yes, you did the right thing, but I want you to do this also on that. Now you can shift the weights, and you can change the loss function, and you can take 200 papers from the last year and try all of them. None of them will help you in that, okay? Because they don't understand the problem. They just, it's like throwing the dice again. But you do one simple thing, and it fixed completely. What you do is you use the deformation method, one of those medical methods, to transform from the nearest neighbor, from the labeled example to the non-labeled. You find the transition point where the classification went bad, from 0, which is what the customer wants, to 6. And then you take these examples, these artificial examples which the deformation created, and put them into the training set, and it's solved. And you can do that again and again until you get 99.99%, meaning like total success on some problems. And that's very hard. Thank you very much. Any questions? If there, please, we have time for one. Speak up, please. We only know to do the following. We know how to apply this, and the other work I've seen also applies this to a large, dense layer, which is one before the classification one. It will work the same, by the way, if the last layer is object detection, okay? But if you don't have that layer, if you have a totally different mechanism, you will have to find it somewhere else, and I'm not sure how that's done. But this mechanism covers, I think, at least all the popular image classification and object detection methods right now. Okay, thank you very much.